right, well, why don't we get started? Welcome everybody to CC Colloquium for today, October 21st, 2020. Just first, one major announcement, Earth and Space Exploration Day is coming up this Saturday, October 24th, from 10 a.m. to 1 p.m. via Zoom. You should have all gotten, here on the CCL email list, which I imagine is all of you, you should have all gotten an email from Kim Baptista earlier this afternoon, just a little while ago, with detailed information to register. So please take a look, check that out. And we hope to see many of you there this weekend. And other announcement is that we're going to have another CC community conversation next Thursday, well, a week from Thursday, a week from tomorrow, at noon. Minnie and the CC leadership team will be giving updates on various things pandemic related and otherwise. So please mark your calendars for that for next Thursday, a week from tomorrow at noon. And I'll just do a quick pre-announcement. Next week's colloquium is a special one. Dr. Robert Braun, who is the Director for Planetary Sciences from JPL, will be joining us, giving us a colloquium entitled Growing Planetary Science Together. So please spread the word about that one. We want to have a great turnout for Bobby, and he will probably be saying some pretty interesting things. So with that, I'm happy to turn it over to Sanj to introduce our speaker.
Thanks, Ariel. First of all, welcome everyone to CC Colloquium. So thanks for joining us. Today, it's my great pleasure to introduce Professor Kristian Finlator from New Mexico State University. I have known Kristian for maybe 8 to 10 years now. And if I have to say one sentence about who he is an excellent scientist, a wonderful speaker and educator, but most of all, he is one of the nicest people in our fraternity. So in fact, I have never had a conversation with Kristian where I haven't learned something incredible, and be it about galaxies, about the universe, or about baking bread. So Kristian really knows a whole lot of stuff, and I hope some of you who had a chance to talk to him today, because Kristian was gracious enough to spend the entire day with us, had similar experience. So let me give a brief bio of Kristian. He had a very illustrious career so far, and more to come. Kristian went to Princeton for his undergraduate work. He graduated in 2000 with a degree in physics, worked with Gil Knapp, Michael Strauss, and others on SDSS data. And then for about 2.5 years, he worked as a software quality assurance engineer for speech recognition in a company in Boston. More importantly, during that time, during the summers, he played frisbee and golf and pool. So next time you meet him in a conference or somewhere else, you can ask him to show off his skills in all of these arenas. Kristian then decided to continue with astronomy. He moved to University of Arizona, our neighbors down south, in 2003. He worked as a graduate student there, worked with Romeo Dove. He overlapped with some of our folks in CC, just Karen Nierman, Patrick Young, Jackie Mumkovich, Chris Groppe. I'm sure they have many stories to tell. But Kristian assures me that he's not at all bitter about his fellow graduate student, Karen Nierman, pulling ranks and taking over a spacious cubicle from him. I am not sure whom to believe. I have to check with Karen for that. So yeah, that's that. So after his great time at U of A and some of the wonderful work he did at U of A, he took a Hubble Fellowship to UC Santa Barbara, where he was there for 3 years. Then he went to Copenhagen to the Dark Center for Cosmology as a Dark Fellow. And after that, he came back to the States because NMSU grabbed him. Good for them. And he is now an assistant professor at New Mexico State University from 2015. Kristian has done a whole lot of work in galaxy formation and evolution. He has focused on phenomena like reionization. He's interested in processes that couple galaxies and the CGM, that's the gas around galaxies, and the intergalactic medium, that's the gas between galaxies. So all how these things are connected, and basically he's running these simulations, getting results from it and comparing to observations, and basically telling us how the universe became the way it is. So without further ado, I give you Kristian Finlator to tell us more about the universe.
Thank you very much to Ariel for inviting me to come give the talk today. And thank you very, very much to Assange for organizing my visit. I've had a lot of wonderful conversations with old friends and with new people whom I hadn't met before today. It's been a real pleasure. I want to talk to you today about work that I've been doing using the overlap or intersection between observations and numerical simulations of structure formation to understand the relationship between galaxy formation on the one hand and cosmological hydrogen reionization on the other hand. And most of my work involves the interface between the intergalactic medium on the one hand and galaxies on the other hand, which is to say the circumgalactic medium. Before I start talking about science, I just want to give a shout out to my collaborators. On the top, I give you the photographs of the 3 students from NMSU, whom I've been working with recently. On the left is Caitlin Doty, who will be defending her PhD in the spring. She's applying for postdocs right now. If you happen to get an application from her, please consider yourself lucky and take it seriously. Samir Kuzmic just began with me, and Farhan Hassan is actually Chris Churchill's student, but I've been working with him on some carbon-4 observation stuff. I also have many non-student collaborators whose names I give in the bottom there. Before I start talking about new science, I just want to talk about some concepts so that we're all on the same page. I understand the audience here is relatively broad. So the first concept I want to talk about is the concept of cosmological redshift. It's been known since the time of Hubble and Humason that the universe is expanding. And if you have a light ray that's traversing the universe, then as the universe expands, the wavelength of that light expands as well. That means that if you have an astronomical source and you can measure by what factor the light from that source has increased in wavelength since the light was emitted, then you have simultaneously measured by what factor the universe has expanded since that light was emitted. And if it's known the rate at which the universe was expanding as a function of time, and cosmologists think they know that pretty well, then you can go from a measurement of how much the light is expanded by in wavelength to the age of the universe at which that light was emitted. This factor by which the light is expanded is usually characterized using this number called redshift, Z here, where it's defined such that 1 plus Z is the ratio of the observed wavelength divided by the intrinsic wavelength. And on the right, I give a nice little mapping between redshifts and the age of the universe that they correspond to. Cosmologists usually use redshift. When they use the word redshift, they're either talking about the change in the wavelength of the light or the age of the universe when the light was emitted. So redshift of 10 corresponds to a light that was emitted when the universe was a little under 500 mega years old, according to a Planck cosmology. A redshift of 5.5 means the light has expanded in wavelength by a factor of 6.5 since it was emitted. It emitted that light when the universe was about 1 billion years old, when reionization more or less ended. Between redshifts of 3 and 2, we're approaching what cosmologists call the epoch of cosmic noon, when galaxy activity and quasar activity were at their zenith. That's when the universe was about 2-3 billion years old. Fun fact, the sun formed at about a redshift about 0.4 when the universe was about 9.5 billion years old. And a redshift of 0 means the light has the same wavelength now when we observe it as it did when it was emitted. That corresponds to a cosmic age of 13.8 gigayears. All right, so a little bit about the history of structure formation. When the universe was extremely young, so between the recombination epoch and when it was about 50 million years old, it was a very boring place. There were not stars and galaxies and quasars and pizza restaurants. There was just a homogeneous mixture of what cosmologists and astronomers call dark matter. That's a phase of matter that has gravity but doesn't seem to do anything else. And it's actually dominant. It's about 85% of the matter in the universe by mass. And then what we would call ordinary matter, what astronomers call baryonic matter, so protons and neutrons and electrons. That was all distributed uniformly throughout the universe to a factor of about 10, to a part in 10 to the 5. In addition, there was light pervading the universe left over from the recombination epoch. That light would eventually expand in wavelength to become what we understand today as the cosmic microwave background. But that's all there was prior to a redshift of about 50. Over the next 100 mega years, mega year means million years, regions of the universe that started out ever so slightly overdense by, again, about a factor of 1 in 10 to the 5, at the recombination epoch, they grew under gravitational instability to become more and more massive. And as matter streamed towards the overdensities, it streamed away from the underdensities. And so the universe became more and more inhomogeneous. Regions that became gravitationally bound acquired their own identity separate from the rest of the universe. And these are referred to as dark matter halos. And I've indicated those with these big black circles here. Dark matter halos are gravitationally bound regions where the universe is no longer expanding. They tend to grow under gravity, sometimes by creating just more dark matter and sometimes by swallowing up other dark matter halos and then growing hierarchically. Throughout this epoch, the ordinary matter or baryonic matter was still neutral and was still cold as far as we can tell. And the light that was left over from the recombination epoch was still streaming around, not really doing much of anything, just getting redder and redder. Over the next 700 million years ago or so, things really started to heat up. Deep in the cores of massive dark matter halos, we don't know exactly how massive, but sufficiently massive, the baryonic matter, or what you would consider to be ordinary matter, was able to cool and collapse under gravity until it had formed very, very dense little lumps, much denser than the dark matter itself that these lumps were embedded in, because dark matter can't cool. Deep inside these lumps, stars were able to form. And once stars formed, they became a new source of light. And the light streamed out of those stars, out of the galaxies, back into the medium between the galaxies and the edge of their host dark matter halos, and indeed even into the medium between the dark matter halos themselves. As they did so, the more energetic portions of these photons were able to strip electrons off of hydrogen atoms and strip the first electron off of the helium atoms, and convert the universe from being neutral to being a plasma. And the vast majority of the universe has been a plasma ever since. As James Rhodes puts it, this is the last time that the average hydrogen atom did anything interesting. This also is a superset of the epoch that's probed by the famous edges result, which you're hopefully all familiar with. So by the time this process had run to completion, there were now 3 phases for baryonic matter. Again, baryonic matter means any ordinary matter for astronomers, and 2 sources of light. For matter, there's the interstellar medium. That's the gas that's between galaxies deep in the cores of dark matter halos. There's the circumgalactic medium. That's the matter between the edges of galaxies and the edges of the dark matter halos that they're embedded in. And then there's the intergalactic medium, which is the gas that's between the dark matter halos themselves. And matter cycles constantly between these phases, and the precise way in which it does that is the subject of very active inquiry right now. There are also 2 sources of light. There was the light left over from the recombination epoch, indicated by the red photons here, if you like those things as photons. And then there's the light that comes out of stars and eventually from quasars as well. The energetic portion of that light is the subject of some discussion in this talk. That's the UV portion, what I call the UVB, or ultraviolet background. Unfortunately, in order to talk about astronomy, I have to introduce 2 more concepts. One of them is magnitudes, the other one is parsecs. Basically, astronomers, whenever they look at a thing that they can see, they have to talk about how bright it is. And we talk about brightness using this concept of magnitude, which goes back 2,000 years to Hipparchus. Things that are bright have very negative numbers, and things that are faint have positive numbers. So the reference point is Vega, which has an apparent magnitude of 0. Things that are brighter than Vega, like Jupiter and Mars, have negative magnitudes. The faintest thing that an 8-meter telescope can see from the ground is about a magnitude of 27. Then there's this concept of absolute magnitude. The absolute magnitude is the magnitude that an object would have if it were a point source located 10 parsecs away. So the Milky Way's absolute magnitude is about -21. That's very bright, but it's totally typical for a bright galaxy. The faintest thing that the HST can see at a redshift of 6 has an absolute magnitude of about -17. That here I'm using absolute magnitude as a indicator of its luminosity. JWST can go a couple of magnitudes fainter, or will be able to go a couple of magnitudes fainter. And then there's this concept of parsec. Parsec is a distance that's very useful for astronomers, and it corresponds to about 3 light years. So the distance between neighboring stars in a galaxy is characteristically a few parsecs, and the distance between neighboring galaxies themselves is a few million times that. So now we've got this framework for structure formation. We've introduced all these vocabulary words like redshift, dark matter halo, all these different media. There will be a quiz at the end of the talk. I just want to introduce these last 2 things here. Metal is anything that's not hydrogen or helium or lithium. If you don't speak astronomy, that's something you have to learn. So everything you ever put in your mouth for food is made of metal. And the UV background, I think I've already introduced. So with the concepts aside, I want to start talking about what I actually do for a living. The tool that I use to study structure formation during the early portion of the universe's history is cosmological simulations. The idea here is conceptually not so hard to describe. You set up inside of a computer a box consisting of all the matter within a cubical volume, maybe 10 to 100 million light years on a side, or parsecs, a million parsecs on a side. Then you put in treatments for all the physical forces or processes that can couple them. So gravity, radiation transport, star formation, heating, cooling, whatever you think you can account for. And then you press go and let the universe evolve and go get a latte and come back a month later and see what happened. The strength of these simulations is that they account realistically for a lot of processes that happen on scales larger than about 100 parsecs. So again, that's about 100 times the typical distance between stars in a galaxy. And they allow you to make lots of predictions that overlap very directly with observations. So you can test them using lots of observations, which is really fun. They also make really pretty movies. The weaknesses of this approach are that they are computationally expensive. It can take tens to hundreds of thousands of computational hours to get one simulation. And they always have these limitations. If you model things inside of a box that is, as in this case, 18 co-moving megaparsecs to a side, then you won't account for the contribution of things that are much rarer than the sort of objects that you would have in the volume. So very, very rare, very massive things tend to be missing. Also, since we don't treat anything that happens on scales much smaller than about 100 parsecs, all the very detailed subgrid physics that has to do with interaction between hot phases and cold phases, the sort of thing that Evan knows a lot about, are things that are out of reach for us. We have to put in guesses for how those sorts of things go, and we do the best we can. So I want to talk about 3 broad questions over the course of this talk today. First of all, how did galaxies form stars during the first billion years? Second of all, how did they enrich and irradiate their environments? And third, how does the circumgalactic medium respond to reionization? So let's talk about the first question. How did galaxies form stars during the first billion years? This is a big question. So I'm going to narrow it down to the much more specific question. What was the minimum mass of dark matter halo in which galaxy formation was permitted to proceed efficiently? In other words, if I have these 3 dark matter halos, and I should mention dark matter halos can have just about any mass. There are good reasons to believe they can have a mass as low as the mass of the Earth, but there are clusters of galaxies in the universe today that have the mass that's 10 to the 15 times the mass of the sun. So they can have a broad range of masses, but which ones of those things have a galaxy inside of them? That's the question that I'm addressing. The motivation for this, you can think of it in 2 ways. Here's the observational motivation. This is a nice paper put out by Roger Yen and by Roger Brinhorst and Haojin Yan back in 2004, where they asked the question, could galaxies be responsible for producing enough ionizing photons to give us the intergalactic medium that seems to be observed at redshift of 6 and redshift of 7? So what they did was they counted up all the galaxies that are seen by HST, and they made some educated guesses as to how many ionizing photons. Ionizing photons are photons that can convert a neutral matter medium into a plasma. How many ionizing photons each one of those galaxies emits? And then they asked the question, can the observed population be responsible for the universe having been a plasma by redshift of 6 or redshift of 7? So if you look at this top panel here, you can see that as you go from bright galaxies to faint galaxies and accumulate all of the ionizing photons that can be produced, Galaxies only down to about 25th magnitude can't do it. They have to produce enough ionizing photons to fall within this region here. If you go down to about the limit of HST around here or so, you could do it. But if you include fainter galaxies, then you can definitely do it. So there's this big question in the extragalactic community right now. How many faint galaxies are there? And that depends on what the lowest mass dark matter halo is that is eligible to form galaxies. The more efficient dark matter halos are at forming galaxies, the more faint galaxies there are below observational limits that are available to us today. So that's the observational motivation. The theoretical motivation is that there are lots of good physical reasons to believe that galaxies can't form in stars, in dark matter halos less massive than some thresholds. There are many processes, and theorists have invoked those processes, more or less the same number of processes, to come up with several different minimum. So for example, by 2007 to 2012, there were some people that were saying galaxies can't form in halos less massive than 10 to the 9 solar masses. In 10 to the 10, there were a couple of papers that put together a model for hydrogen cooling in dark matter halos and hydrogen cooling based star formation to estimate that galaxies can't form in halos less massive than 10 to the 10 solar masses. And in 2010, Nicolas Boucher put together a very clever paper in which he showed that if galaxy formation is inefficient in dark matter halos less massive than 10 to the 11 solar masses, then a great many observations of a process called galaxy downsizing can suddenly be reproduced by your models. So there's a wide range of assumptions that go into models, and it would be nice to see what the data actually say. There's another paper that came out that was put together by Stephen Finkelstein, an illustrious graduate of ASU's program last year, in which he allowed this uncertainty to vary within his modeling to see what their constraints were. But I'm interested in the question, do observations actually constrain this minimum? And I would argue they absolutely do. So let me step you through this figure and how it works. What we've done is we've gone into this simulation, which produces many galaxies of many different luminosities. And we've made what's called a luminosity function. A luminosity function is really just a histogram. On the y-axis is number of galaxies per bin in luminosity per volume. And on the x-axis is luminosity. That's absolute magnitude, but absolute magnitude is the same thing as luminosity. So the points with error bars represent the observed luminosity function. So there are lots of faint things and relatively few bright things. Faint things are here and bright things are here. So you can see there are more faint things than bright things. And then the curves represent the simulated galaxy luminosity function under a range of assumptions. So first, let's talk about the red curve. That's the actual simulated luminosity function that comes directly out of the simulation. What we did after producing this was we asked each galaxy, what dark matter halo mass do you live in? And we rank ordered all the galaxies by the dark matter halo mass that they live in. And then we started throwing out dark matter halos of increasing mass and all the galaxies that they inhabit. And as you throw out dark matter halos of increasing mass, you start to throw out more and more bright galaxies. And so we did this and asked the question, at what point have we thrown out so many dark matter halos and their associated galaxies that we now introduce attention with observations? So the red curve shows the intrinsic luminosity function directed by the simulation. This green curve here, the second one from the top, indicates the luminosity function under the assumption that dark matter halos less massive than 10 to the 9 solar masses can't form stars. So that we've introduced an extra threshold within the simulation and post-processing to make this curve. This CN curve here tells you what the luminosity function would be if you ignore all galaxies in dark matter halos less massive than 10 to the 9.5. This introduces an extra threshold of 10 to the 10 and so on. And you can see that as you increase the mass threshold for forming galaxies, you start to introduce a tension. So quantitatively, at what point have we introduced a significant tension? To evaluate this, we use something called the Bayesian information criterion. We treat the introduction of a dark matter halo mass threshold as an extra parameter. Use the Bayesian information criterion to ask at what point that extra parameter is ruled out by observations. So on the y-axis is something called evidence against the minimum. And on the x-axis is the actual minimum that's introduced as an extra parameter in post-processing into the modeling. So that you can see here, by the time we get to about 3 by 10 to the 9 solar masses here, the number of galaxies that are being removed from the model is starting to introduce strong evidence against that extra parameter being appropriate. And by the time we get to about 5 times 10 to the 9 solar masses, we have very strong evidence against that parameter being appropriate. That's a redshift of 6. What that means is that the model in which the minimum halo mass for galaxy formation is greater than 2 by 10 to the 9 solar masses is ruled out at redshift of 6. So if you have a model in which galaxy formation is forbidden in dark matter halos less massive than 10 to the 10 solar masses, redshift of 6, then I will tell you that the UV luminosity function observed in the frontier fields by HST rules that model out, unless you're being extraordinarily creative with your efficiencies. And as you go to less massive thresholds, the evidence becomes weaker. You also have weaker evidence at high redshifts just because those luminosity functions are shallower. So there are some models that are in the published literature right now, which are ruled out by the current data. And of course, as the models improve and as the data improve, we will be able to revisit that and see what tighter constraints we get. That's all I wanted to say about star formation. The next question I want to talk about is, how did early galaxies enrich their environments with metals? Remember, a metal is anything that's not hydrogen, helium, or lithium. That's a big question, so I'm going to focus in on the narrower question of how the observed line incidence of carbon-4 absorbers actually constrains feedback models. And by constrain, I mean, does it rule out feedback models? So the observational motivation for this is, you come at it in many different ways here, but this is one that I think is very inspiring. The image here is of an ordinary galaxy, sub-L star in astronomer speak, of a galaxy at about redshift of 7.5. So it emitted the light that we see today when the universe was about 700 million years old. This galaxy is strongly magnified by a foreground cluster, and it has an enormous amount of dust in it. Dust is made of metals, so that means the universe was making lots of metals by a redshift of 7.5. So how many metals had it made, and where were they? This is something that's predicted directly by the model here. So let me show you what this plot goes through. On the x-axis is redshift, and redshift is converted to time in the following sense. This is early. This is late. This is when reionization was just beginning. This is the moment when it ends in this particular simulation, and this is a redshift of 5. So time increases to the left, redshift increases to the right. The black curve here indicates what the metal mass fraction is in the intergalactic medium in the simulation, normalized to what it is at redshift of 5. So at redshift 5, it has 1, and at redshift of 10, it has a value of about 1.5%. So what this model predicts is that the universe was already producing lots of metals by redshift of 10, but only about 1.5% of what it produced by redshift of 5. This looks linear, but remember, this is a logarithmic axis. So the universe actually produced about 50% of the metals by redshift of 5. 50% of the metals that have been produced by redshift of 5 got produced since redshift of 6. So this is a prediction, this rate at which new metals are being produced and injected into the intergalactic or circumgalactic medium. That's a prediction of the model. We'd like to test that. How can we test it? Well, we test it by using a technique called absorption line spectroscopy. And if you work with Sanch or Evan, then you know about this technique. If you don't, then let me review it for you. Suppose that I have a good, powerful telescope here, represented by this little sketch down here. And I use it to take a very high resolution spectrum of some bright thing that's a long way away in the universe. Of course, I'll learn lots of information about that bright thing. But if there happens to be any gas between the telescope and that bright thing, and there always is, then that gas will start to take out some of the light from that background thing. It'll produce absorption lines. And if that object is at cosmological distances, then at every point where the light goes through the universe here, it expands in wavelength. So if there's absorption owing to something like this, at this position here, then exactly the same ion that produces absorption here will produce absorption here, but at a completely different wavelength in my spectrum. So I can distinguish how much absorption there was owing to precisely the same ion at a range of different distances, owing to the happy fact that the universe redshifts the spectrum as the light traverses the universe. So if I happen to have a strong galaxy, a bright galaxy here that's near to my sight line at position A, and a faint galaxy that's far from my sight line at position B, then you might imagine that this would take out quite a bit of light from my background object here from position A. This would be absorption. And this object here, this faint object that's far from the sight line, would produce less absorption at position B. And if you're clever, then what you can do is you can identify the disabsorption owes to, for example, carbon-4, that is to say triply ionized carbon or silicon-4 or oxygen-6 or whatever ion it is. And then you can start to learn about the thermal state of the gas that's producing that absorption. And in most of the time, that's the only thing you ever know about this gas. You don't see anything glowing in emission, you only see it in absorption. Most of the gas in the universe only reveals itself through absorption. And this is actually a synthetic spectrum. This is a fake carbon-4 absorber here. Carbon-4 is very popular with astronomers because it has what's called a very strong oscillator strength, which means it casts very dark shadows if there happens to be something behind it. So it's very easy to see an absorption. So how do we make absorbers in the simulation? You take a simulation volume and you cast a sightline through that simulation volume at an angle that's oblique to the boundaries. And then at every position along that sightline, you ask the question, what is the density, the temperature, the metallicity, and the ionizing background, which is permitted to change from one position to the next. Once you've done that, you can actually create a fake spectrum that indicates how much absorption there is owing to every ion that you're interested in along the line of sight. You can even account for instrumental noise and the instrumental response function, and you can make things like this. The bottom three panels here are fake spectra. They're fake absorption spectra owing to carbon-4, that is to say triply ionized carbon atoms, silicon-4, another ion that's popular with astronomers is triply ionized silicon, or carbon-2 is singly ionized carbon. They are all relatively common ions in absorption line spectroscopy. So these are fake, these are synthetic absorbers here, but they look reasonably realistic. I tried hard to make them that way. I won't go into the distinction between the different curves here, that's not important. But what I do want to talk about is how to characterize these things. Just the same way as when you look at two stars, you want to ask which one is brighter. If you look at two absorbers, you want to say which one is stronger. And there are two ways to characterize the strength of an absorption system. One of them is called the equivalent width. The equivalent width is just a measure of the area under this curve here. If you've done what's called normalized the continuum here, then you can just measure the area inside the absorbed region of this spectrum here, and you can quote a number, which will have units of either kilometers per second in velocity space or angstroms if it's in wavelength space. So that's a number that's very easy to measure directly from a spectra. Two people who have the same spectra ought to measure the same number for that. Turns out that's hard to predict though. The number that's easier to predict is a different one. That's called column density. So column density is how many ions per square centimeter on the sky are there in the along my sightline that produce that dark shadow in the spectrum that I'm looking at. In order to measure column density, you have to do something called Voigt profile fitting, which is a nightmare, especially when you have a complicated profile like this one. It has units of ions per square centimeter. So equivalent width is easy to measure, hard to predict. Column density is easy to measure, difficult to measure and easy to predict. So naturally, if you've got two different ways that have strengths and weaknesses, the best thing is to use both of them to make your comparison. So a few years ago, when I started looking at this, I asked the question, okay, how many strong absorbers, how many weak absorbers are there per unit volume in the simulation? How does that compare to observations? The triangles with arrow bars there in the bottom panel indicate basically just a histogram. Again, it's just a histogram, number of absorbers per volume per strength. Strength in this case is indicated by column density, so number of ions per square centimeter of carbon-4. If you look at a comparison between the observations here given by these triangles with arrow bars versus the simulation, which is this magenta shaded region here, you can see there's pretty good agreement for what we would call strong absorbers. But then at the weekend, the simulation seems to be overproducing the observations. And this can't just be statistical error because the statistics are excellent here. So this was an early suggestion that the model was actually a little bit too efficient, either at producing metals or at ejecting them into the circumgalactic medium. So there were some weaknesses for this study. First of all, we now know that simulation produced way too many stars. We also know that the ionizing background, which converts carbon from carbon-1 all the way into carbon-4, was too strong in this model. It was also a relatively small simulation volume, so you could always argue that there are some things that are not taken into account because I didn't take into account large voids, for example. And finally, the column densities here from the simulation are relatively easy to measure, but observationally void profile fitting has its limitations. So you'd like to do the same comparison except in equivalent width space. A few years later, that's exactly what Farhanul Hassan did using a complementary data set. He measured the distribution of absorbers as a function of their equivalent width now. So on the y-axis, again, it's just a histogram, number of absorbers per equivalent width per volume. And on the x-axis is equivalent width, in this case, just given in units of angstroms. And he made this nice histogram here, this column density distribution function. Those are the triangles with error bars again. And we decided to compare it to an updated model, which has a lot of corrections. It now produces what we know to be the correct number of stars. In astronomer speak, it has the correct stellar mass function at the redshift of interest. It has the correct UVB amplitude, so there's the correct number of ionizing photons flying around between galaxies. It's not wrong anymore. And the simulation subtends 15 times the cosmological volume, so it's much more representative volume. Also, we're using equivalent widths. Unfortunately, you get exactly the same result. So sometimes you try very hard to make a problem go away, and it just won't. Takeaway is the model is definitely producing metals and it's definitely ejecting them into the circumgalactic medium, but it seems to be doing it in a way that overproduces weak carbon-4 absorbers at redshift of 3. So closer to about halfway between reionization and cosmic noon. I don't know what the reason is why the model produces too much carbon-4. Possible explanations are we're just making too much carbon, period. The trivial application of this idea would just move the normalization of the column density distribution up and down, which would then introduce a discrepancy at the bright end or the strong end. Could be that the enriched gas is too diffuse, that is to say it's not clumpy enough. Clumps introduce more low ionization ions, so that would reduce carbon-4. Dust depletion is something that's not taken into account. In the real universe, there's dust, as I showed you in the motivation for this section, and dust tends to take carbon out of the carbon-4 state into the cold state. Or it could be that something's wrong with the UVB. So all these things are possibilities that I'd like to explore once I have a little bit more time. But I want to leave that aside for now and start talking about the UVB. So how did early galaxies irradiate their environments? This relates to the question of whether galaxies actually drove cosmological hydrogen reionization, because if they drove hydrogen reionization, you would think they would also have an impact on their circumgalactic media, which are closer to the galaxies themselves than the intergalactic medium is. We'd like to understand what that relationship is. So a narrower version of this question is, how do the statistics of metal absorbers reflect the intensity and spectral hardness of the ionizing background? What are intensity and spectral hardness? Let me just define those things real fast here. If I were to make a figure that says how many photons there are flying around between galaxies as a function of their energy, it would look something like this. There would be fewer high energy photons and more low energy photons, at least in the UV portion of the spectrum. The intensity is the normalization of that distribution. So if I increase the intensity, then I increase the amount of photons that there are in all energies. Hardness is the slope of this. That is how many high energy photons per low energy photon. So if I change the slope of this from being like this to being like this, to being flat, this would be a hard spectrum, and this would be a soft spectrum. And then this one here that I've sketched is somewhere in between. So the question is, does the CGM let us learn about these things? I won't talk about ionization equilibrium. I'll just mention that carbon-4 and silicon-4 are ions that you only achieve in gas that's irradiated by a relatively intense and/or hard ionizing background. If there's no ionizing background, you expect to see something more like carbon-2 or silicon-2. So back to column density distribution functions here. What I'm showing here on the x-axis again is column density. On the left is carbon-4, on the right is silicon-4. And on the right, on the y-axis, again, it's just a histogram, number of absorbers per strength per volume. The crosses represent observations for the abundances of these ions at redshift of something like 5 to 6. And then the peach, I guess I should say salmon shaded region represents the prediction of a model that I put together in 2016. So in 2016, the model underproduced both carbon-4 and silicon-4. indicating either that there weren't enough metals or that the UVB wasn't intense enough at the redshift of interest here. So that's a starting point for this discussion. Between 2016 and about 2019, I made a lot of improvements to the model. I made sure that it produces the correct number of stars. The ionizing background is more realistic. It produces a more realistic Lyman-a Forest if you're an astronomer. Made a lot of improvements like that. So once I'd improved the model, you can ask the question, okay, then what happens? This is what happens. Once you produce the correct ionizing background and the correct number of stars, then you kind of automatically produce the correct amount of silicon-4, which is kind of encouraging. That means that silicon-4 is kind of a probe of the progress of hydrogen reionization and the progress of star formation kind of put together. But there's almost no difference in terms of the carbon-4. So carbon-4 is still dramatically underproduced. Again, this model produces, as far as we can tell, the correct ionizing background, a reasonable reionization history, the correct stellar mass function, and even the correct silicon-4 distribution, but still not nearly enough carbon-4. So what gives? How can this possibly be wrong? I was a little bit disappointed about this because I'd been wanting to do other things besides with carbon-4 besides just make column density distributions. But I got to thinking about it and I started to wonder, does it matter how the light actually gets out of galaxies? And so I started thinking about how that actually works. So here I want to introduce two different ways for how ionizing light gets out of galaxies. These are two extreme models for ionizing escape. On the left, the scenario is as follows. You have a bunch of stars that are forming deep within the core of a galaxy, and they're surrounded by gas, which is opaque to ionizing radiation in most directions, but completely transparent in a few directions. These are like windows and these are walls. Wherever you have windows, the light gets out completely unattenuated. And so the ionizing spectrum that you see in these directions, whoopsies, in these directions is the same as what's intrinsically produced by those stars. That's the ionization bounded case. And this is the model that is implicitly or accidentally assumed by just about every reionization modeler. And no one attempts to ask the question, does the escaping ionizing continuum have a different shape than the intrinsic ionizing continuum? However, it could. And in particular, it would if you had what's called density bounded case. In the density bounded case, you have the same stars, but now instead of being surrounded by walls and windows, they're surrounded by, think of it as like wax paper. It's translucent. It's barely transparent enough that photons can get out that have the energy to ionize hydrogen, but higher energy photons can get through much more easily because they have a shorter wavelength and therefore a smaller cross section for interacting with that gas. So with exactly the same stars, producing exactly the same intrinsic number of ionizing photons, you can get a much harder ionizing continuum coming out of such a galaxy. And you can normalize the spectrum that it escapes in such a way that you would get exactly the same Lyman-a Forest. So same stars, same reionization history, same Lyman-a Forest, totally different at high energies. The only way you would see this is by looking at high ionization photons. So I got interested in the question is, if I modeled this in post-processing in the simulations, would it make a difference? And the answer is yes, it does. Once I add that post-processing fiddle under the simulations, then I find that the blue curve here represents the carbon-4 column density distribution. And for the first time, I can actually more or less reproduce the observed abundance of carbon-4 at redshift of 5. As a check, we can ask whether I then break the good agreement with the silicon-4 distribution. And you can see in the right panel here that silicon-4 is still reproduced. Silicon-4 is a lower ionization ion than carbon-4 is. It has a lower ionization energy, which means it's less sensitive to that really high energy light that is preferred in the density bounded escape scenario. So I found this very exciting. I'd like to continue exploring it in the future. But one thing you could ask is, okay, is there another observational test that we can use to distinguish between these scenarios? And the answer is there absolutely is another test, and this will come online with JWST. The concept behind it is as follows. Suppose I've got two scenarios. In one scenario, galaxies let out relatively little of their hard ionizing light. In another scenario, the galaxies let out quite a bit more of their ionizing light. In the scenario in which galaxies are very efficient at releasing their hard ionizing light, you require relatively few galaxies to produce a given carbon-4 absorber because the galaxies are bright in the light that makes carbon-4. Therefore, if you count galaxies in the vicinity of carbon-4 absorbers, then you should be able to distinguish models in which galaxies are very inefficient at releasing carbon-4 producing light versus models in which they're very efficient. So that's what's represented by this figure here. Let's just look at the red dashed curve here and the green dashed curve. So I apologize to those of you who are colorblind, but the red dashed is short dashed and green dashed is long dashed here. So the red dashed curve indicates the case where you've got very efficient releasers of hard ionizing energy. And in that case, you will require relatively few galaxies here in the vicinity of a strong carbon-4 absorber. So this y-axis here is number of galaxies within 250 proper kiloparsecs of a strong absorber as a function of their magnitude, bright, faint. This is cumulative. You've got relatively few. If galaxies are efficient at releasing that ionizing light that produces carbon-4 absorbers, then you have relatively few. If they're inefficient, then you need more galaxies to produce the same carbon-4 absorber. And so you expect more neighboring galaxies around a given carbon-4 absorber. So by counting galaxies in the vicinity of high ionization absorbers, you should be able to distinguish between the scenario in which galaxies are efficient or inefficient at releasing their hard ionizing photons. This is impossible with JWST. You can't do this science because even with 100 orbits, you can't see too many galaxies that would be neighboring around absorbers. But with JWST, it should be child's play. Even one absorber should have of order 5 to 10 neighboring galaxies down to an absolute magnitude of -15. So this should be very exciting. There's another way in which you can look at the impact of the ionizing background and its spectral slope on the circumgalactic medium. And that is, instead of looking at silicon-4 and carbon-4 separately, you look at a higher order statistic, which is the aligned absorbers. So look at places where you have carbon-4 and then ask the question, do I have silicon-4 at the same place in velocity space or position along the sight line? And if so, let's plot the ratio of those two things. So that's what's plotted here. This is work that was done by my student, Caitlin Doty. This was her first project. This is carbon-4 column density versus silicon-4 column density. So this dot here represents one absorber, which was in the synthetic absorber catalog. This is its carbon-4 column density. This is its silicon-4 column density. Here's another one, here's another one, and these are the observations. So if you look here, this in this model here, all of these models use exactly the same hydrodynamic simulation. I just swapped in and out different ionizing backgrounds and made the predictions for the catalogs. In this model here, the ionizing background that is assumed is the industry standard, if you like, ionizing background is the Hart-Medal 12 background. It vastly underproduces carbon-4 at a given silicon-4 column density. So it's not nearly hard enough for the CGM as it seems to be observed. In this model here, small scale spatial fluctuations are accounted for such that the ionizing background is stronger near galaxies, as it should be. The light is stronger if you're sitting right next to a light bulb than it is if you're on the other side of the room. And this is the case in which the ionizing background that's released by galaxies is hard, characteristic of what you would expect from quasars. And so what you can see is in this case, you get the weakest agreement, here you get somewhat stronger agreement, and here you get somewhat stronger agreement here. So the takeaway from her study was, first of all, that the circumgalactic medium absolutely is sensitive to the slope of the ionizing background. Second of all, that a harder ionizing background does seem to be preferred. This doesn't mean that the background has to come from quasars, but it needs to be harder than what it is, at least in the case of the Hart-Medal background. Of course, she wasn't content with just making plots and requiring you to hold your thumb up to the screen. She came up with a statistical model and showed that the likelihood for the QSO's model was much higher than that of the other two models here. So this is very nice work. The takeaways from this section, the incidences of carbon-4 and silicon-4 and the statistics of aligned absorbers, they are sensitive to the history of star formation and to the slope of the escaping ionizing continuum. The data favor a relatively hard UVB. You might get that from a density bounded escape scenario. You might get that from some other scenario which produces a little bit more hard ionizing flux. But the data don't seem to require QSO-driven reionization. And if you want to talk about QSO-driven reionization, we can talk about that, but the takeaway is that it's not favored by any of the modeling that's available right now, and for the most part, not favored by observations either, which is why I focus on galaxies. So for the last portion of this talk, I want to talk about how the circumgalactic medium actually responds to the progress of reionization. And in particular, I'll talk about the line incidence of neutral oxygen absorbers. Background to this is, prior to the hydrogen-1 reionization, hydrogen and helium were neutral, and all the metals would have been in low ionization states. So oxygen-1, silicon-2, and carbon-2, and magnesium-2. This is what you expect in places where the universe hasn't been reionized yet. In places where it has been reionized, you expect your metals to be in higher ionization states like silicon-4, for example, or magnesium-3. So the theory for this goes back to 2002, and it's been revisited many times since then. There continues to be an idea that you can use metals to trace the progress of hydrogen reionization, which is very interesting. Another observations that seem to be pointing in this direction as well by George Becker and Alex Codorino, among others. So this is just the one figure that I want to point to for this section here. Let me step you through it. On the x-axis here again is redshift, going from low redshift to high redshift. So this is early times, this is late times. On the y-axis is the line incidence of oxygen-1 absorbers. So this is the number of oxygen-1 absorbers per volume that are stronger in this case than 0.05 angstroms in equivalent width or 0.01 angstroms in equivalent width. And I want to just focus on this bottom curve here because that's the one that's observable right now. These are observations by George Becker. These are the same catalogs of absorbers. If he divides them up into 4 bins in redshift, he gets the green curves here. If he divides up in 2 bins of redshift, he gets the black curves here. And so what you notice both in the theory and in the observations is, first of all, that the abundance of O1 absorbers does not do this. It does not go up in time. The number of metals in the universe is strongly predicted to go up in time because the universe makes more metals as it makes more stars. And yet the number density of oxygen-1 absorbers is predicted to be flat. So there's some sort of competition between producing more metals and then ionizing more metals owing to the progress of reionization. Second of all, there might even be a little feature here. The theory predicts that there is a feature where the O1 incidence drops right at the moment when the H1 neutral fraction goes to 0 owing to reionization completing. So that's what the theory predicts. And observations do seem to have detected a feature. If we just look at this black things here, you see again that the oxygen-1 incidence is increasing during an epoch when the total metal incidence should be decreasing. And there may even be a strong evidence for an increase here and here, which would be consistent with reionization having happened somewhere between here and here. So both observations and theory seem to suggest that the low ionization absorbers are an interesting probe of the progress of H1 reionization. If we were able to go to even weaker absorbers, we would probably see a stronger signal. And there's qualitative support for that in the observations, but I'm not showing that here. So the takeaway from that is, yes, absolutely, recent measurements do seem to indicate qualitative agreement with predictions in 2 ways. First of all, the O1 incidence does not grow in the way that it should if O1 just traced metals. So there's some interesting competition between enrichment and ionization going on. Second of all, there does seem to be evidence for a feature around redshift of 5 to 6 that's consistent with the completion of H1 reionization. All right, so what have we learned? First of all, halos more massive than about 2 × 10⁹ solar masses kind of have to grow galaxies. If you want to propose that they don't, then you're going to have difficulty reproducing the observed UV luminosity function. So far, models seem to overproduce weak carbon-4 absorbers at redshift of 3 and then underproduce all of them at redshift of 6. We can make some progress with that by invoking this density-bounded escape scenario, which is not the standard assumption, but it does seem to have some promise, at least in terms of this observable. O1 absorbers can and should and do seem to notice H1 reionization. There's definitely room for improvement in terms of both the modeling and the observations here, and I look forward to that over the next decade. Here's some things that we would love to know. We'd love to know what ionizing emissivity is from any stars, any stellar population. We don't really know what ionizing emissivity is even from solar metallicity stars because you can't take a spectrum of an O star in the galaxy. There's too much neutral gas along the way. The Ulysses project is attempting to make progress with that. The wavelength dependence of the ionizing escape fraction. No one's looking into this to good approximation, and I've shown you an argument that it might be critical for closing the gap between observations and models in at least one case. And of course, we'd love to learn the mass and redshift dependence of the ionizing escape fraction as well. The small scale structure of the CGM is a big source of stress for anyone who models the CGM because no one's doing it properly. So that's a computational frontier. And I haven't mentioned it here, but the galaxy mass metallicity relationship is something that I continue to be interested in and definitely will be illuminated by observations from JWST. So that's all I wanted to say right now. I'm certainly open for questions.
Thank you. So we are a little tight on time, but we have time, I think, for a couple of questions. So if folks want to, as usual, either raise your hand and I'll call on you, or type in questions in the Q&A. I'll be happy to moderate that. So just raise your hand if you want to ask a question or type away. Oh, we have a couple of questions. So first of all, Lucia Perez. Lucia,
Hi,
you are allowed to talk.
Hi, can you hear me?
Loud and clear.
Great. Hi, I'm Lucia. I'm one of James and Sangeeta's students, and this was a really cool presentation.
Thank you.
So I'm curious about the counting method you were speaking about. So how would you deal, like, is Poisson noise for the counting of galaxies an issue in this case? Like,
yeah, it absolutely is. If you only have one absorber and you expect to find 5 galaxies around it and you find 4, it's very difficult to say whether you rule out the model or not. You'd have to do this for a lot of absorbers. But there are plenty of absorbers known, and JWST should be able to survey the fields around bright quasars. In fact, it's going to do that. There are already a lot of proposals to do this. So I'm hoping that by combining predictions from 10 to 20 absorbers, we'll be able to start to distinguish between different models.
awesome, thank you.
Thank you.
Great. Roger, hold on a second here. Roger Windhorst has a question. Where'd he go? There he is. Oops, nope. There you go. Roger, you should be able to talk now.
Okay, thanks. Can you hear me, Kristian?
Loud and clear. Thank you, Roger.
Yeah, thanks. Excellent talk. So what do you think about a role for weak AGN to help with the reionization? Could you also model that? I know that becomes a lot more linear, non-linear in these simulations, but it would be very helpful to know. As I think we have evidence that at least the redshift 2 and 3, the AGN seem to dominate the Lyman continuum production.
Yes, certainly below redshift of 3, I don't think there's any dispute about that. They must dominate Lyman and continuum production. By about redshift of 4 or 5, they're at or less than 50% of the Lyman continuum production. But you're absolutely right. I mean, there could be, there could be very low mass AGN that are buried deep within these galaxies. Certainly, that's a possibility, and it would help with understanding the incidence of carbon-4 absorbers at very high redshift. I haven't tried to model that yet. It would be possible to do, but it would be interesting to ask what other observable I could use to anchor such a model other than just the carbon-4. So you could interpret the need for extra hard ionizing flux in many ways. You could say there needs to be binary stars instead of just single stars, which is all that is accounted for in this model. You could say density bounded escape. You could say low mass AGN as well. It's a very good possibility. I'd like to think about what other observable there would be that we could use to distinguish between these different scenarios.
Okay, thanks. Yeah, nitrogen 5 perhaps, but that will be
yes,
tough.
Nitrogen 5 if you can observe it. Yeah, absolutely.
All right, we have one other question here, and then I think we'll have to say farewell. Timothy Carlton asks, thanks for a great talk. In your halo modeling, do you model any environmental dependence to galaxy formation efficiency?
So yes, in as much as that's accounted for in 18 megaparsec simulation volume. So I mean, the simulations, they form the dark matter halos self-consistently, and the galaxies form in them. And so we already know that within the simulation, satellites are much fainter for a given dark matter halo mass than central galaxies are, as they should be. So the ability for the simulation to self-consistently account for the broad scatter and the relationship between UV luminosity and halo mass is one of the strengths that we brought to bear on our estimate of the minimum dark matter halo mass. It's by no means correct, the scatter between luminosity and halo masses in the simulation, but we do the best we can.
Great. And on that note, I think we have to wrap up. So thank you very much for a lovely talk. And everybody, please be sure to join us next week. There's also a question for Rolf that I'll send to you afterwards here. So please be sure to join us next week also for a talk by Bobby Braun from JPL. So virtual applause and some real applause here. Thanks.
All right. Thank you all.
Thank you, Kristian.
Thank you, Sanj.